Or there are some parts that you don't have rain now. Okay. So this is what we have.
It's raining in Kaduna.
You should have added the condition. Because we didn't know that it was because of the rain. Otherwise, I would have left office long ago. I'm seeing the office and the rain is here.
Oh. Sorry. So for us, we are doing something, and then if part weather condition was part of it, and then they were saying it, so I said, okay, let me cancel. But yeah, you are right. Maybe I should have added it. Yeah. Okay. So let's see. So this is just descriptives, okay, to help us understand the relationship. Okay. So what you want to model is MPG. So here, one thing that should be of interest to you is how does MPG relate to the other variables? The more the correlation between it, the more or the likelihood that that variable will what? Will predict MPG quite well. Okay, so if you look at MPG, let's say from here, which the first column, which variable is so related, that is heavily related to MPG? Yes. Please, I'm listening to you.
Cylinder.
Cylinder. Okay, so someone says cylinder. Do you agree? Please, everybody should have we have about 10 or so variables. So you should choose your own and justify. Yes. Please, just nobody is right, nobody is wrong here. Let's just discuss. It's a discussion.
Can you sorry, can you come again with the
Yeah,
instructions for
so
us?
you have this, okay, this graph. So when I take MPG, for example, MPG and cylinder, you see that the relationship is either this, the one below the MPG, or at the top of, on the right hand side of it. That is
Yes, sir.
cylinder versus what? MPG.
Yes, sir.
Good, okay. And it goes along with it. So what is above the diagonal, right, is the same as, is like a mirror image of what is below. So that's the graph
Sure.
you are seeing. So for example, the one at the bottom left is the same as one at the topmost left, the topmost right.
Yes.
Yeah. Good. Now, so if you look at this, which variable is heavily related to MPG, whether in a positive manner or a negative manner? Yes. Please, let's. Oh, my dear friends, let's hurry up. No one.
Hello,
Yes.
Prof. I'll take horsepower. I think the graphs, the one above it, the horsepower and right next to it, all of them are positively related to MPG in a way.
Horsepower and which one?
I will take horsepower as positively related, and I also take weight to be negatively related.
Weight and MPG.
Yes, weight is negatively related to MPG, the correlation.
Okay.
When horsepower will be positive.
Horsepower. Okay. Okay. So horsepower and MPG is here, and then horsepower and MPG is here. You said it's positively related.
Yes, Prof. Positive, yes.
Are you sure?
Horsepower and MPG.
Horsepower and MPG.
Okay. So that's where the pointer is. So if it's that, then it's negative. Sorry.
Okay, good. Okay, so you mean horsepower and then you said H. Which one again? This. What about displacement?
I talked about weight. The
weight.
beauty.
Good, yeah. So you realize that weight.
Displacement is negative.
Weight is also what?
Weight is also negative from what I see here.
Yeah. Okay. Is everybody okay? So if you look at those variables, they are in some way they will be what? More related to what? The
Hello, sir. Hello, sir.
yes.
Yeah, please. I just joined and I'm a bit lost.
Please come again.
I just joined the class. I'm a bit lost.
So what were you there yesterday?
Yes, please.
So we are discussing what we did.
Okay, sir.
Yeah. So we are just discussing what we did. Remember, this thing showed that we are none of the variables was actually related to the
MPG.
MPG. Do you remember?
Yes, sir.
Good. Yeah. So that's the what we are trying to do now.
Okay.
So and what I was saying was that if you look at that, what it means is that you will say all of them are not significant and throw all of them away. Which is, the model is as good as just a constant. It's just a constant plus some random variation. That was how it looked like, but that's not the case. All right. So we are using this correlation matrix to help us decide. But as I said, in fitting the model, you can start with all the model, which is like what we did, or you can start building it from basics, which is forward selection. So what we were doing yesterday was a backward selection. We have the full model and we try to remove some of the variables. Okay, so now what I want you to do, everyone, is that let's start. So we are saying that weight, horsepower, displacement, they are, and even I think drought, right, are heavily related with MPG. So let's start with a model that start with one of those variables. Okay, so do that and let's see, which means, but this correlation we can also do. Before we do that, let's see how we can also get even elegant clause for correlation. So there is a package. So correlations. There's a package called plot. So install it.
Sir, we can't see your screen.
You can, a moment. So start installing core plot. Start. So the package is called core plot. So it's core plot. This one. Okay. So you install. Then with core plot, you can get a so you go here and then you look for core plot. So library core plot. Okay, then you. So with this, we can now get the core plot function. Then we take our empty cast. Okay, so there are methods that we can use. One of them is circles. Okay, so when we do a circle, you get a meta circle. The matrix is in -1. I think we have a problem with okay, let's see. Core plus should have, is it the categorical variables that, so it's like a graphical display of matrix, confidence interval, the details, pay great attention to it. You can visualize general matrix and so forth. So core, I think we have to, is a correlation matrix, sorry. So we need to find the correlation matrix first before we put it in. Okay, so how do you find the correlation matrix? You just use core. Okay, so let me call it core.mat. Should be core empty cast. Okay, then I put this core.mat to it. There we go. So you see, sometimes you may even remember what a function is, but you can get stuck along the way. Did you see what I was doing? So the first one, I got an error. Because sometimes you may forget. I thought, okay, core plot empty cast. So then I need to find out, how do I get around this? So the key thing is that I need to get to look for what? The help function for using the core plot. So I did that. I came to help. And then I checked here. Please, are you listening? Because this is very important. Otherwise, you can get stuck anywhere. So core plot needs core. That's the data you are putting in. Then the method, the type, and so forth and so forth. Okay, so you can do so many things. So, and then I come to down here and check the arguments. The argument should be a core. What is the core? It's a correlation matrix to visualize. Now, is MT cast a correlation matrix? Please, I need you to answer.
Hello, Prof.
Yes.
It's not a correlation matrix.
It's not a correlation matrix. It's the actual data. So then I need to now go and do what? And get the correlation matrix for that data. And that's what I did with the core. So after that, then I'm in a position now to what? To get the correlation. Is everybody okay with this?
Yes, sir.
Yeah. Okay, so then we get this. But if you explore, you can get, so you see on the diagonal, they are all deep blue. What is deep blue here? The scale is here is 1. That's what I was saying. So as you get over here, -1 will be very much. So you will see that all the ones towards this color are the negative correlation. Do you remember weight and the MPG? Okay, MPG and cylinder, MPG and display. So this is just like what we did the previous one. But if you want elegant graphics, rather than the other one we did, these are some of the things. Is everybody okay with this?
Yes, sir.
Good.
Yes.
Okay. Now, so you can explore, okay, when you, I mean, there are so many of them that you can explore here. Yeah, so circles.
Sir,
Yes.
please, I can see the circles, like they have different colors, but then why are the sizes also different?
Yeah, so the size is also signifying the extent of the correlation. So the smaller it is, the less correlated they are. So if you see on the diagonal, those are the bigger ones, right? So the color and the size move together. The higher the correlation, the more deeper the color, and then also the size of the circle. There are so many that you can use. You can also use a number. Okay, you can use even pi. You can display it in pie chart. So check, if you check the method, you see all of them. We can also use number. Then it gives us something like this. Okay. So if you juxtapose this with your other one, you realize that it's the same. Unless I pop it out. If I pop it out, so you see the color, you see the way the color is. If the color is deep, if the correlation is high. So this or those one gives you quite an easy way of presenting your correlation between them, and that helps you in giving your the analysis of it. Okay. Any questions? So you can explore some of these things, but essentially, where do we want to get to? Well, it means that when we are doing our regression, one way to go around this is that we start with, let's say the displacement is around 0.85. Look at, and then what else did you say? Displacement with MPG negative 0.85. So if you look over here, they are all negative. Weight is 0.87. And then cylinder and displacement are almost the same. Then you come to HP before you go to DRAT. Is that okay? And so forth. So we can get a simple linear regression. Let's say SLR Okay, LM, the formula is, then the data is empty cars, right? And then we can do what is it? MPG on what? Let's say the most significant is weight. So let's see whether this gives so look at it. Will you say this is a significant predictor of the MPG? So let's all do it and just try and explain what they mean. Is that okay? So what I'm saying is that do this, okay, and look at the model and compare it with what you did yesterday. So this, would you say that weight significantly determines the MPG or the variation in the MPG?
It can determine the variation in MPG at 1%.
Yeah. Okay. So if you look at it, the coefficient of weight is actually significant. You see it almost close to 0. So if we are doing a hypothesis test, we'll reject the null hypothesis that the coefficient of weight is 0, which is highly significant. Look at the R squared. That is 75%.
Yeah, it explain the dependent variable as MPG.
Yes.
At 75%.
75%.
Yeah.
So it means that 75% of the variation you see in the MPG can be explained or can be attributed to what?
It's as a result of
This
weight.
The weight.
Independent
Good.
variable.
Yeah, the weight. So now you realize that this is quite significant. Okay, we can't throw it out. That's why I said, but for the bigger one, you realize that we were not getting any significant results. And the reason is that some of them, and if you look at the correlation here, look at, for example, the correlation between cylinder and displacement. Do you see the correlation value? Almost perfect, right? Please, can you see?
Almost 1.
Yeah.
Yes.
Yeah, 0.9.
Good. Yeah. So
Almost 1.
that introduces what we call multicollinearity.
Yeah.
Yeah. And that's why when you put all of them together, it's like they are not explaining the variation well. Okay. So basically, this is what we mean by this one. We are doing forward selection. Now I can go on and do another one. Call it, let's say, SLR1, and then I try and add another variable. But I'll check which variable, what it's the weight. You see, even if I just select that, it's highly related. Let me check. AM. DRAT is also quite high. HP, horsepower, is a bit low concern. So I'll try and add horsepower and see what will happen. And we realize that horsepower is also related to what? MPG 0.78, so it's a bit high. So let's see what will happen. Okay, then we check the summary. Okay, so now look at this. All the two variables are important. Weight, horsepower, they are all important. Do you agree? You look at the
Yes.
multiple regression, R squared adjusted, we move into the 80s. So this is just to tell you that you can actually build a model on your own. Okay, and you can automate this as well. So these are some of the things you'll be doing.
Prof.
Yes.
Hello, Prof.
Yes.
Please. Yes, please. Aside using the p-value.
Yes. Please go on.
It should be rejected, or it should be dropped in the model, or it should be added.
I was losing you. Can you come again? You said aside using the p-value. What
heavily.
else?
Yeah. Is there any other way we can determine the significant level of a model?
Yes, you
aside
can.
Using the p-value.
Yeah, you can also use this, but it means that you have to go and read the t-value and compare this with it.
Okay.
Just like you were doing in exams, then they give you what is it? So T with some degrees of freedom and so forth.
Okay.
What you in exams will give you like 4-figure table, then you go and read it. That's it. So that's why we usually will use a p-value, because it's straightforward to do. But if you have to report this, you must report your entire coefficients, the estimates, the standard error, and so forth. Don't just record only the p-value, but the whole of this must be provided.
All right.
Okay. Yes, any other questions? So I think this will explain how multicollinearity and the model building as well. You can go on to help you select the best model.
All right. Sir, please, Prof, please, the code wrote SLR. That's simple linear regression, right?
Yes, but I mean, you can use anything. I just use the abbreviations. Because this one is just.
I don't know whether the model, the regression table that we have here is a multiple regression. I want to know whether still use the same code.
Oh, the LM is the same. This is a function.
LR.
The LM is the same.
It's linear model, right?
Linear model, yes. That will be the same, whether simple or multiple. Yeah. And as for these names, I am just giving it, so I can give any name at all.
Okay. All right.
Okay. Please, any question? Okay. Now let's move on. Okay, so please take note of this and how you.
Hello, Prof.
Yes. Yes, please go on.
Please, in dropping a variable.
Yes.
Aside the pairwise correlation that we just did.
Yes.
for us to establish collinearity level.
Yes.
In the multiple linear regression table like this, aside the p-value,
Yes.
is there a way we can also drop it using the coefficients?
Yes. One other
Maybe
way
they
is
are
to
all
also compute
statistically
what we call variance inflation factors.
and the VIF.
Yes, the VIF, and then you use that one to determine which ones are collinear.
They are collinear.
Yeah,
I think the rule of the thumb is what are the benchmarks
so
when
I
it comes
think
to the individual
above
variable
5.
in the
Yeah.
VIF table?
Above 5.
Okay,
In some cases
all
they
right.
say 10 and so forth, but I think above 5. Yeah, should be fine.
Okay. All right.
All right.
But in case in a multiple linear regression table, Prof,
Yes.
if all the variables are, let's say, like what we did yesterday,
Yes.
you see that most of the variables are statistically significant percent.
Yes.
Most of them are statistically insignificant at 5%.
Yes.
So it means that let's say I can decide to use 10%. So if I use 10, that means one is statistically significant.
Yeah, maybe
So
one or
in that
more.
case,
Yes.
if I'm dropping the variables,
Yes.
in that case, if I'm dropping the variables, if let's say I benchmark it at 10%,
Yeah.
so it means that I have to only use one variable in a model.
Yes, one variable. But you see, it would have been
so
weight, and you realize that when we came back, we realized that weight is highly significant.
Yes.
Yes. So essentially, why we are doing this is to tell you that when there is this multicollinearity, even your best variable may be masked because of its interaction with another variable. Its significance may be masked. Yeah. And that's the essence of this exercise.
Okay.
Yeah.
So in situations like, let's say, like your main independent variable is having is highly correlated with another variable.
Yes.
It means that maybe you sacrifice the other variable
Yes,
for
yeah.
main independent variable, right?
Yes, yeah. Because whatever you can get in the other one, it's being reflected in another variable. So it's good to maintain one.
Yeah.
So the
Okay.
fewer,
All right, that's
the
fine.
better, or the merrier.
All right. Okay.
Okay, so let's move on. Okay, so basically that's it, and then so here the first one, if I track back, we have also a test of overall regression. So in the case of this one, you look at this one, right, and remember the down one. So if you look over here for the simple linear regression, the whole model is actually significant, right? 1.29, right? Is that okay? Please, are you there?
Yes, Prof, you're here.
Good. Okay. So yeah, so that's it. Then so in the simple linear regression, it's almost the same as what testing whether this one is significant, the weight is significant. Okay, so but here you see we can test the individual ones, and then we can test all of them put together. Okay, so this one too is highly significant. So the overall regression is what? Highly significant. Do you remember what you did yesterday? So that we can do it again. Maybe we call it MLR, and then that we change this to what? A dot, and then we do that all of it. summary, and so look at putting all these variables, about 10 of them. We got our multiple R squared to be what? 86. Look at even the adjusted R squared, 81. And compare it with what we got from the 2. Do you see what is happening? Please, are you following?
Yeah.
So, when we use only 2, we are getting even better explanation in terms of the adjusted R squared than this one. And
there is efficiency there.
Yes, there is efficiency. And secondly, the adjusted R squared will only increase if the variable you are adding on is one not correlated to the other independent variable, and also is heavily correlated with it checks the correlation of the additional variable that you are putting and the response variable, in this case MPG. Okay, so that's what the essence of this exercise, that we can have just some few variables doing better work than what the entire putting everything together. And that's why in model building you can do both sides, check whether both sides, whether forward selection or backward selection. Yes.
Prof, you just run. One, you use most of the independent variables.
Yes.
Yes, I realize that it is also showing that the p-value is significant at 1%.
Yes.
And we realize that the individual variables, they are not statistically significant. Most of them are not statistically. So why is it reflecting that the entire model is statistically significant at 1%?
Okay.
Because most of the individual variables are reporting that they are not statistically significant.
Yeah.
So why is it that the general p-value is saying that
significant,
the model is statistically at 1%?
You have a point there. Remember that any variable you add to the model will increase the R squared. So look at the multiple R squared. So if I have a model that is explaining almost 87% of the variation, it must be what? Significant. That's why the overall F statistics is significant. However, is it prudent? Is it optimal? Because mind you, if this is data collection, it means that you have to spend money in collecting data from how many? 11 variables. However, you can even achieve even better results if you only collect data on what? The weight and the HP alone. Yeah. So those are some of the things you need to consider.
In variables, we achieve efficiency there as compared to the one with the plenty.
All of them, yeah. And mind you, cost, implications, and a whole lot. If it is in health, maybe you are now taking blood from someone, recruit people, follow them, and so forth. So some of this, even though we are doing it here, in practice, it's very severe. So you have to collect data on 9 variables, and each of them, maybe you have to spend money. Some of them, and you started with sampling. Some of them may cause harm. Some will result in money. So, for example, you crash test the car. When you crash it, that's it. Do you get it? So that cost if just the weight and the horsepower is giving you that, why go and crash a car to test the airbag?
Mm-hmm.
Yeah, so those are the important issues in such these things. So we are not going to spend so much time here because you will actually do this even in more details in your other classes as well. But this is to show you that whatever we are doing here is important. It's important that you get to know how to do it, especially in this setting. So that's it. Please, any question, or otherwise I should be preparing to move into the other thing. But just to yes.
Hello, Prof.
Yes.
I was thinking that those planes we added to the model, since they're not statistically significant, it should rather the entire p-value. I was thinking it should rather affect the p-value.
Yeah, but
so
check
that
the p-value.
Now go
look at the extent of the p-value here, and let's go up.
Yeah.
Check the p-value.
Okay.
So you see that the 2 is more significant, almost twice.
More close to 0.
Yeah, almost close to 0 also. If you look at it, e to the power, the 7, and that's almost twice the value of the exponent in negative sense. Okay, and if you look at the F statistics, the larger the F statistics, the better. Or the better the significant. Look at 69 as against 13.
Yeah. Okay. So that's what you should tell us. That's there is okay. I get it.
Okay. So one more thing we did was the plots, right? Okay. So remember that I'm doing all this again because, as I said, you need to find data and be doing. It doesn't mean that everybody will do a multiple regression. Okay. Yeah. So what we have done, if you reproduce it, well, it's good, but it's not the best. We want you to explore more, right? Okay, so these are the values that are the graphs that yesterday you were trying to explain. So here we want all of them to be scattered around the 0 line, right? And yeah, so if there are trends, it indicates that it is not sufficient fit. So some of you were struggling to explain. So this one, if you look at it, there is some trend, but it is not profound, right? Okay, so those are the middle part around 20. You realize that these two values will be pulling the curve downwards. Okay, and over here you don't see much over there, so that's why there's a drop in values, but it's not profound. The sample size is not so large, so you don't see the kind of graph we want to see. And then secondly, Chrysler Imperial and Toyota Corolla, they give very what? Different, they are outliers, right? In terms of their fate around. I think the Toyota Corolla, there's another car there, but it's maybe if we pop it out, we will see it. Which car it is? A Fiat 12. Fiat 12 something, yeah, and so forth. So those cars, they give indication of deviation from the model. Please, is everybody okay with that?
So Prof,
yes.
This is the diagnostics test that you perform.
Yes.
And how does it affect the choice of the model we use, or the choice of the estimation techniques that we use?
So these are
Because
descriptives.
I know that.
Yes.
Okay.
Okay, you can go
Because
on.
I know we perform pre-diagnostic tests to determine the estimation techniques that will be employed. So onto this diagnostic test that we've performed, how is it going to inform the estimation techniques that either we are going to use GMM, we are going to use a panel correct test standard error, whether we are going to use whatever estimation techniques? How would this pre-diagnostics or the diagnostic test that we perform, how will it advise us or give us a clue as to?
So when you the diagnosis is usually when you are done with the model. So it helps you in deciding should you keep this model or continue to look for something better. And whether
so these
the
are
assumptions are satisfied.
diagnostics.
Yes. So whether the assumptions are satisfied. So this one we needed to fit it and test. The assumptions are that the residuals versus the fitted plot, the residuals should have what? Evenly spread around it. There shouldn't be trend and so forth.
So, Prof, with this one that has the scatter points around the fitted line, what does it suggest?
Which one? So this one,
the graph we are having here, the residual.
Is it a slight trend, especially getting to the central part, right? Yes, but it's and then it's also showing you the values that are outliers and influential, so to speak. So it is the Chrysler that is actually pulling the line towards itself. Do you see it? And then when you go to the other end, the Toyota and the Fiat too are up there, and it seems to what? Pull the curve towards itself. In between that 20, even though they were not, you see those two values down there. Those are also pulling the curve towards itself. Okay, so that's what really happens in it. And for a smaller sample size, you tend to have this. If it is larger, and then it's well scattered around the space, then the better it is.
Okay, Prof. So, Prof, is this post-estimation diagnostics, is it applicable in secondary data as well and primary data? Like, can you apply it in all the
once you have
primary data or
fitted a
secondary
model,
data?
usually a model, whether regression or other models, will have some assumptions. And so when you finish, you must check. Some assumptions may be checked before you even fit the model. Right?
Because most the finance research that we don't do this residual fitted diagnostics.
Yes.
We just test for multicollinearity, using the pairwise correlation, and then the VIF, and then we do heteroscedasticity, and then those other.
So those are all assumptions. Some of them you can see it here, but remember this one is just descriptives. Or what you are saying, we can also do a formal test of hypothesis. So we want the residuals to be normally distributed. I can just get the residuals and actually test whether they are so the receipt will give me all the residuals. So these are the residuals. So this I have to check whether they are normally distributed. Do you see the Imperial, the Chrysler Imperial? Look at its value. You see it's quite high. Look at the Fiat 128. That's the other one. And then the Toyota Corolla. The rest, you see that they are within. Okay, so that's it. So this, we can also plot it either a histogram, and so there are several ways of looking at the diagnostics. But this is not really a linear model class. As I said, the sample size is quite small, so there exists some skewness in it, and that's also what you encounter in this one. That if all of them were evenly spread around the zero, okay, then you realize that you won't have it to approach normality. But this one, there's a bit of a distortion, and that's what you see in the residuals. So there are so many things. The residuals I can check, are they normally distributed or not? A formal hypothesis and so forth. And then the variation, I can also check whether it's constant and so forth. And you can even see it through here, whether the variations change entirely. And you can talk about standardized residuals. So here we are looking at it in such a way that if it is good, all the points should cluster around the line. And the line must be at the 45 degrees line. So this one, if you look at it, Chrysler, Imperial, Toyota Corolla, and Fiat, they are pulling this curve towards itself. Okay, and then you have some other low values, and these are the two values we see in that are distinct at the bottom of the residual versus the fitted graph. Okay, so it's good, but there are some deviations, some cars that deviate from the model. Here, standardized residuals, right? And then the fitted values. It's just like the other one. It's not much. Then the scale versus the location, right? And if you look at this one, you don't want to see trend. Okay, look at the Chrysler Imperial, Toyota, and Fiat. They still exhibit that sort of outlier stuff around it. And then lastly, the residual versus the leverage or the Cook distance. And this, you see the Toyota, the Chrysler, you see they are quite distinct from the other values. And so forth. So the Cook distance also allows you to see influence, the influential stuff in there. So some may be outliers, but they may not have much leverage or influence in terms of the diagnostics. All right. So that's it with it. So at least for these models, you should be in a position to do all this and that. There's also the logistic regression. We did some examples in there that you should also be able to do and report on it and so forth. Please, any question before we now move into our main area? This is a diversion for us to understand our concepts well before we do our...
Hello.
Yes.
The diagnostics that we just did.
Yes.
They are all necessary when you are writing your research report. Like you have to report on all these things.
Yes, but it depends. Okay, so sometimes, well, maybe if you are writing a paper and you are limited for space, you, instead of giving a graph, you could just report on the normality test of the residuals. And now you can just give a test statistics and a p-value, and that suffice.
Okay.
Yeah. So instead of getting all these graphs to occupy space. But in a thesis, you want more pages and so forth. So yes, it is allowed. You can bring all those your tests and so forth. So it basically depends on what you are doing and what really is.
So you report it after the descriptive statistics.
Yes.
You report all the pre-diagnosis right after the descriptives before you get into the regression.
That's no. So there are some that you need to fit the regression before you can talk about it, and there are some that you can check before. So, for example, you are saying that the y values must be normally distributed. I can test that before I do it. Do you get it? Because it takes its normality from the epsilon, the errors. So those ones I can do it before I even um, start with my test. But whatever you get over there will translate into the model as well. Okay.
Oh, okay. All right.
Okay.
Thank you.
Okay, you're welcome. All right. Okay, so now let's get started with our Spark. Usually it won't work here as I said. So I go back. Connections, preparing connections. Spark. Okay, let's see. Did they work? The following object is marked by package. Okay, good. Alright, so let's see. I go here, I copy my. Did I? Okay, it works. Okay. So yes, okay, can open. Let me just go and set my JDK and rerun this. Okay. Okay, so please, are you done? Okay, so from what you were given yesterday, so we are going to the chapter 4 of the Mastering Spark, right? So within the Spark framework, there are in multiple regression, there are several, I want to, so ML, let me show you. The regression framework. So ML regressions. Okay, so let me. Sorry, ML. So in the all this, you have all this in terms of supervised learning, so many, okay, regression trees, survival analysis, supervised pipeline, ML summary, standardized, and so forth. So this is what, I mean, in terms of Spark, that's how this is done. So in our regression, even though we are using LM, here, everything is start with what? ML, like the machine learning, sort of. That's how it is. So if you are doing K-means, GLM, generalized linear regression, and so forth. That's everything that you have. So this is the summary, right, of all the functions in there. You can also get it from, let me get you from this folder, mastering Spark. Okay, there's appendix. Yeah. Okay, so let me show you this. So, as I said, this will help you in all your other courses. Okay, so if you come to the mastering Spark, if you check the regressions, right? Okay, so you have other classification problems, decision trees, gradient boosting. So you do this in your machine learning. So once you have this background, you should be able to do it. For the logistic regression, you should, because we've gone through it. But linear support, vector, machine, multi-layer perceptron, naive Bayes, and so forth, you do them in machine learning. So I'm not going to talk about it. We just did regression so that you will have a feel of it and be able to at least do one of it. So there it is. So these are the functions we are going to use. So if we want linear regression like we are doing, we'll use ML linear regression. Clustering, all those things, you can do it in there. And you see everything is what? ML. And so frequent pattern mining in your machine data mining class, you will come across all that and so forth. Okay, so these are some of the functions, the ML library functions, okay, that are supported in Spark. Okay, so later on in those your classes, you must have a use. You are using random forest, you can transition seamlessly into what? The Spark or this environment. Please, is everybody okay with this? Is everybody okay? With where we want to get to? Okay, so now let's get back to our R and try and implement this and see that if you know the basis, then the rest will just what? Follow suit, right? Okay, so what we want is ML linear regression. So there it is. So question mark. So the first time you use any function, what do? Do question mark and look at what? The way it is used, right? So you perform regression using what? Linear regression. And it is Spark ML. So you have X, you have your formula, you have fit intercept is true, elastic net, parameters, regression, and so forth, weighted, column, loss, error, square, error, solver, auto, a whole lot. And when you come down here, you see X is what? A Spark connection, right? Okay, so or ML pipeline. We will do pipeline later on, okay, and a bit of how to do clusters. Okay, so you'll be introduced to it, even though we don't have that sort of high performance computing where you have several clusters. But with this, you should be able to transition to it in case you have some at your workplace or you find yourself doing this later on. Okay, so that's it. Then the formula will just be like what we've been using before and so forth. So the rest you can just explore what. But the concepts are basically the same. Nothing really changes. Okay, so we have to go back and do our CAS. If you remember, CAS, we said it's what copy to XE empty CAS, right? Empty CAS. That's what we did. Yeah, and then if you go to your connection, you see empty CAS there, right? Okay, so now if we were to do the multiple regression in the Spark framework, we cannot be doing it in the using the LM. It has to be this. Okay, so our X is equal to CAS. Okay, and then we have our formula. If you want to write it in full, will be MPG. Okay, then this. If we put dot here, it means all of them, right? All of them. And then we do this. You see, this takes a bit of time, right? To give you the results. And the reason is simple, it's due to what? The connections. Okay, so still it can't get to then, but the formula is what? MPG, coefficient, this and so forth. You can go back and check with the results of what we got earlier. Okay, so the intercept, the 12 point something, there we go. So you see 12. The next one, cylinder, -1,1, displacement 0.13. We can go there and check and so forth. And of course we can get what any other results that we want to get. Of course you can do the simple linear ones. Okay, if we want to do any simple linear ones, you can do it. So we can do that of the weight quite easily. It will give us, there it is. Okay, and if you want, we've already seen those diagnostics stuff and so forth in here. So is any question? So let's try it. Everybody should try it. ML, make sure you let's assume we
so Prof.
Yes.
Hello. Yeah, please. So now you are doing the same linear regression that we did previously.
Yes.
You are doing the same thing.
Yes. But now, whatever I'm performing links me to Spark. So the computations, everything, the data is being held over there. Right? And then all what I do is that I get my my commands. It connects it to the database. That's why it keeps long a bit, right? And then I get my results. Yeah. So the results is now displayed over here. But you realize that there are a bit of in terms of what you will get, you see this one is simplified. You don't get the results as you got from the, that is the same because we got 0.72 root mean square error like that, but some of the things we expect that you can get it on your own. So for example, the what is it, the adjusted R squared and so forth, you can easily compute it on your own or get it from it. So one way you can also get the coefficients and their standard error. So what do I do? So SR, if you do over here, you have all these. Okay, so what if I want the coefficients? There it is, right? There are so many. The results is a list, so you can check the model, this, so explore the response. And so for model, coefficient, summary. So
Hello, Prof.
Hello, yes.
Prof. Yes. He said what you are doing now
Yes.
helps our results to be saved on Spark.
The results are not saved in Spark.
Okay, they are held there.
Yeah. So okay. So the principle, you shouldn't lose track of it. That the idea is that for the data to sit on your laptop, memory space and so forth, when we connect to Spark holds the data. Then you do all your computations and then I'll collect the results.
Okay.
Yeah, so you free memory, you free space and so forth, so that you can actually get to use the R.
So, Prof,
Yes.
please, what command did you add to this one that made it to be held in Spark?
Oh, so you connect to it.
The Spark we connected earlier on.
Yes. But you have to do it if you have. So there, this one, this.
Yeah, we connected it. That's yesterday. That's long ago. That's yesterday. So I wanted to know the commands that you are using right now. Like, no, we are still using it. Like
Okay,
it's still there.
right, because for me,
I'm still using the same file.
Yeah.
If you don't off it, is there something that okay, maybe you are doing other works, so you
Yes,
have to
I
switch
do
it off. Okay.
to use it to teach and so forth. So usually I disconnect, and then when I come back, that's why every time I'm connecting to it.
All right. Okay, that's fine.
So you copy the data to it, you see the data, then you can do so. So you see all these values can be obtained, right? Coefficient, standard error, deviance, residuals, explained variance, features column, labels column, mean absolute error, mean squared error, distant p-values, prediction column, predictions, and so forth. Okay. So just try on your own how to get some of these results out, like summary, what have you. Please, are you okay? Have you been able to do it?
It's prof. We are fine.
Okay. Okay. So check the data, the other data set, and let's check whether you'll be able to get it. So if you check your stuff, you need library page 5. No, page 3. You need to download the file. So download file. Let me see. That's 4. So you need to get that done. So just copy the content over there and paste. But you must be connected to the internet, right? Okay, copied data set. Right, okay, so let's see whether we're able to download. So it's quite big, I think 53 megabytes. So depending on your internet connection, it may take some time. But even if it doesn't come, you should be in a position to. So mine is in progress, right? So this data is in GitHub, and I hope that you know about GitHub. So you can create accounts over there and store your stuff. I have my own account. So for example, when we write a paper and the data you want to store it, okay, so that people can have access to it, you can do it in GitHub. People do store lecture notes and so forth over there. You get it for you to be able to have access to it and so forth. Okay, so we can unzip, unlink, so that it doesn't link it over there. So now we have this data within our okay, let's see what comes out of it. So the profiles, that's profiles, and then read.csv, then data /profiles. So this is some data on okay. So you see now we have the data profile of the people here, and it's quite a large data set on people on a dating site. So the age, the body type, the diet, drinks, whether the person drinks or not, socially, often socially, drugs, never. Some do not answer. Education. So about 31 variables. And essay. I am a chef. This is what that means. I am a workaholic. So and so. They are all looking for partners and so forth. So, yeah. So basically, these are some of the data sets you may come across: social media data or log on data set from people. So whatever you put over there can be gotten. So speaks English, Japanese, Poli, this Farsi. About 60,000 people, right? So the data is about 60,000 user profiles from OkCupid. It talks about some biographical data sets include age, sex, height, job, right? And then education, behavioral, about drinks, drugs, whether the person smokes, and so forth. Then also there are essays about themselves, and if you look at it, it's almost 10, right? Just so people will get attracted to the person. The height data, we've talked about it. Income as well. People state their income, but you shouldn't trust those things. That's just if there's no verification. So for dating now. Okay, so let's look at it. And then we can have, so here we can do some classification and also regression. Okay, so the classification, we can check to see whether we can predict someone's, there's work, right? Work is about job, okay. Status, so it's either you are working or you are not working. So job, like this. Some say income, medicine here. Some do not even give anything about it. Some other and so forth. So whether you are working or not working, okay. So if you look at this data set, it will not be structured in a way that you can just take it straight away and what? And use it. Sometimes you need to what? Do some sort of that's why we did data wranglings, right? To be able to do wrangle the data in a way that will help you to work on it. So two things that we will be dealing with from here is, so two problems that we want to solve from this side is one. So regression problem. So the regression, we want to see the essay length. So we want to be able to predict your essay length. And two, for classification, so the classification problem, we want to see not working, and that will be binary, right? So definitely either 0 or what? Or 1. That is working or not working. So this is the problem we want to solve from these from this data. Please, have you been able to download it and put it into this side? So copy this, don't type, it will take a long time. So copy from the what I sent you yesterday on the on the WhatsApp page. Are you with me?
Yes, bro. Yeah.
Yes, Prof. Yeah, with you, sir.
Okay.
Very much with you.
Have you been able to download it? I am waiting for you. So there's a slide that I did. I'll have to send it to you people. But it's just from what I sent you, so we should get the same. So you need to load the data. So loading. Remember what we did is that the data is now stored on our computer, not Spark. So if you come to Spark connection, you see it's only empty cars. The data we are dealing with is in R now. So it means that we need to clean it and then splitting. We want to be able to split it into what we call test training and test data. Load. Okay, so how do we do this? So in the what was sent to you, you see this is slightly different from the way I did it here, but let's see. If I'll send you the codes. Let's see if okay, so let's see profiles, XC, then escape, option, multi-line, then mutate, essay length. So we want the essay length. We just take essay 1 up to essay 2. Separator is this. Then we scale the age, and then we remember income and area not working is as dot integer unemployment. So the mutate ends, and then we can now split the data. Okay, so that's spark.read.csv. Escape. Okay, see, then we get this. Okay, so let's see if it works. Unexpected. Was it that? Yeah. This was not like okay. And then minus. So when you copy, it's a bit. Let's see what goes on. Okay, so that works now, I think. So because these missing values are always removed in the SQL aggregation function, use it to silence this option. So now we go to connections and the profiles are there. Do you see it? So now our profiles, we see it in the so that data is now in Spark, diet and so forth. So this, you can't type it now unless I send you the slides, which I will do, and then I'll send you the codes once we are done. Okay. Then now we need to split the data into, so this function SDF split, so we are splitting this data into training. 80% to be used to train the model and 20% to test it. Then we set a seed so that we get the same results, right? If you remember. So here we'll say split the data into training and test group. Right, okay, so we do that. And that is done. So now OKC train is this, OKC split is this. Okay. All right. Now, what else? Yeah. So now that you have this, we can implement, let's say, our regression. Okay. So our regression, we want to check whether your age is related to your essay length. Can we predict the length of your essay based on your age? Maybe the older people, they are lonely, so they are able to type more than the younger ones. So that's the sort of thing we want to be able to do over here. Oh, I should have been writing this at the top down. Oh, no. Okay, data says it should be in between here. Please, are you following? So we want the data. So here, what did we do? We downloaded the data, but it's in just from another side. So we do all this, the download the file or download it. You can unzip because it's a zip file, and then you unlink it. Okay, then it goes into a directory called data, which is just temporary, and then you read it from it into an Excel sheet. We want to be able to address two problems: regression, which is essay length, and then classification not working. Okay, then so we need our library then Spark Connect, this we've done it already, so there's no need for it. I comment it out so that when you get it, you don't need to worry yourself again with it. Right. Now, then here we have to read it. So this is where you are reading it into Spark. So the first two lines will read the data, then escape is like that, okay? Because in the data you see all this, right? If you go into the data as we did earlier, you see all this in there. Then mutate. So here, what we are doing, nchar is the number of characters. So it means that paste to is like you are, just that's the name, put it there. So once you put it there, you are pasting. The separator is a blank, right? So your SA0 length, and then your SA1, SA2, SA3, we put all of them together, then we count the number of characters in there. So that's the SA length. Then the scaled age is that you standardize the age, right? So in this case, somebody's age may be negative. What it means simply is that the person is what? Younger than the average age. Then income. So if your income is negative, it means what? We convert it to what? Not real. Okay, other than that, we get a numeric part of it. And then not working is also as.integer. So job in days. Of course, that will be, if it is true, it will be 1. If it is false, then it means you are not working. And that's what we saw from the data earlier. So the empty ones will be what? Not in there, so it will code it as what? Not working, 0. Then after that, we now see one more function which is called SDF random split, which means it is a function that you can use to split data set into what? 2 parts. One that is to be used for a model, and the other that is to be used for what? Testing, right? So you do so, OKC train, and then a test set, and that's it. Okay. So that is a loading, and then splitting. We are done with that. So this goes up here. Loading, splitting, and yeah. Okay. And then, so now we are in a position to fit our model. So we are doing simple linear regression, just like we did earlier. And then with this, we can then call it a night. Okay. So how do we do it? Well, let's say SLROKC will be ML regression ML linear regression. So, and in this case, it will be our OKC train. So the training one, we take that data, and then what we want is the formula. And the formula will be what? What do we want to do? We want SA length as a function of the scaled age. One may ask, why are we scaling it? Scaled age. The spellings must be right, otherwise it will not work. So let's see whether this works. What is causing the problem? Okay, C train. Okay, see, okay, it's gone now. We have a problem. Apart, the value negative of the string cannot be in the big because it is malformed. Correct is value per the sentence or change its target. I use strikers to tourist malform input return instead. Let's go. Okay. Okay, so let's see, skilled age. Okay, see. So let's see what happens here. Oh, it's already here. The skilled age will be somewhere here. Okay. We do not have, okay, I now understand. So let's see. The OKC, the mutate. Excellent. Okay, so let's see this. Good. Let's see. Okay, I need to check on this why the mutate is not it works, but you can't find essay length and so forth in here. Okay, so okay, so I think maybe we can close. I'll work on this and send you the code. So basically what we were trying to do is just to be able to read from a data, create new variables, okay, from the already from the variables that we have, and be able to get filter regression on it. The first one, we're able to do it on a small data set, but this is more like what you get in a big data framework to work with, and how to do all these data wranglings and be able to fit models in it to do so. So you realize that the number of characters in there, we are creating that. You know, we put them together, we count, and then we'll get the values, and then also we'll be able to use our own mutate by using the mutate function to now get a new data set and be able to work on it. Okay, so basically that's it, and I think next week we'll continue with it to get to fit our models and be able to be able to fit model, comment on it, and so forth, so that you will be able to now work on practical data sets once we give you your assignment for the end of the semester, and be able to also defend it. Yeah. Okay. So I think, please, any question? Other than that, we can call it a night, and we'll meet, God willing, next week.
So, Prof, the defense, are we going to defend the feedback, the results that we are getting, or we are going to defend the codes?
Both. And the interpretations.
But we want to defend only the results.
No, you have
the codes here. We'll find. You see the codes there.
Yeah.
There is AI. So
no, but you
so
must understand.
Makes the work more easier.
You must.
Yeah, we understand.
No, if you understand, why are you saying we should not ask you?
I think it should be. You should tone down. You should tone down when it comes to the codes. But yeah, I think that's my suggestion. Because the codes, Charlie.
So you should know whatever you are doing. Other than that, when there's a problem, you won't be able to fix it. Because as for programming, you always encounter problems.
Yeah, the AI always fix the problem for us.
That's your thinking. Then you are being controlled by the AI. We want it to be the other way around. You can't. There are some things that you can do for the AI to just sit there and maybe just hallucinate, and you might think you've gotten the right answer.
Yeah.
Okay. So if you don't have any question, then I think we can call it a night.
All right, bro.
Thank you. Thank you so much. We are grateful.
Yeah, okay. So,
Thank you very much, bro.
have a nice evening.
Doc, will you share the inquiry tonight?
Yes, I'll share it.
Please, the course and the video.
The video. Okay.
And the video.
All right.
Yeah.
Okay.
Okay. Thank you so much.
Have a good